So good afternoon. Yes, afternoon, and happy Friday. I'm still getting used to teaching on Fridays. I haven't taught on Fridays in, gosh, like 8, 10 years. So this is kind of familiar but new. But nonetheless, today the plan I don't is to spend as little time as possible in the slides and the majority of the time in the Pac-Man code. And we will look at how some of the theory plays out with respect to admissibility, dominance, and a notion of ultimately what is the effective branching factor. And so we'll use, well, I don't want to reveal it until it's time to reveal it. Okay. We'll use the Pac-Man example to talk about that. So how's everybody doing? Good? Happy for Friday. We're gonna get snow again. It's like, oh no, at home, literally still have like 4.5 foot tall snowbanks, and there's like no place to put the snow. And so for the dog, every day, I'd spend about 2 hours digging trenches in the yard for the dog to run around. And so I'm not too enthusiastic about getting more snow, but nonetheless, it is what it is. Welcome to Massachusetts, right? All right, so why don't we get started? The reading has not changed. The reading will change next week. You'll certainly be kept aware of that. It's in the syllabus, so there's no secret to what that is. Homework number one has been released. There are two different versions, the undergrad version and the grad version. Again, I tried to do the assignment to the grad students, the 4+1 students, as a subset, and the undergrads as a subset, but something in Canvas just doesn't work, right? I did a tester and somebody gave me feedback they can't see it, which they were supposed to. It's supposed to work. So the other implementation you'll find is that if the assignment is not for you, your grade for that has been set to excused, right? So please, if you're enterprising to do the grad version, please do the undergrad version if you're an undergrad taking, registered for 210. And then you're happy to explore and challenge yourself to your heart's desire. Likewise, if you're a 4+1 student or registered for the 310 version, please do the grad one first. And then to your heart's desire if you choose to do the undergrad one. But they're excused for those cohorts for whom it is not intended. That's the only other implementation in Canvas to select subsets because the other one didn't work. Okay. All right, any questions? No? All right. So one of the exercises did I hit record? It's like in muscle memory. I think I did. Let me just, yeah, I'm recording. Okay, I don't remember. Um, One of the exercises that we did concerned two heuristics, H1, the count of misplaced tiles, and we gave the 8 puzzle problem as our example, and H2, the distance to the goal location for each of the tiles, namely the Manhattan distance. And what we saw for this first try from the starting state in our search tree was that H1, okay, required you to search more subtrees rooted in that first set of children, which you encountered when you explored or expanded the frontier. And so that effective pruning, we said, we tried to draw the relationship to this idea of the search contour. And we said with a larger heuristic, you're pushing the search contour forward faster and in effectively pruning some areas of the tree, reducing the number of nodes that you count, which is a reduction, a multiplicative reduction on time. And so we talked about this notion of the effective branching factor. And the effective branching factor solves the following equation. And a B star value, we said that's close to 1 is a better effective branching factor. And so we talked about this reduction, it's multiplicative in the time complexity, the number of nodes that you encounter. And we gave this table, and this table's in the book, and that table compares the performance of A star search with the H1 heuristic, more simplistic, albeit admissible, which we went through in our exercise, and the H2 heuristic, which is also admissible. And as you can see, the number of nodes generated for the H2 version is smaller than the number of nodes generated for the H1 version. And that also plays out with the effective branching factor. And both of them, because they're informed search, they both beat breadth first search to jar your memories. Any questions? No? So this should be old hat by now. Okay. And so we said that for all cases, the H2 heuristic dominates the H1 heuristic. That is, this value of H2 is always larger than the value for H1 for all of the nodes in our state space. And so that means higher H values, and you have to preserve admissibility. Consistency is the stronger case. If you have admissible heuristics and your decision is about which one you're going to go forward with, choose the one that has the higher values. And in the better case, the one that dominates. Okay. All right. Any questions? No? Okay. And so what we're going to do as an exercise, we're going to make use of question 7, the food search problem, and we're going to tinker with a heuristic, not the heuristic. There are many different heuristics that you could implement. And we're going to look at different versions of this heuristic. We're going to think about admissibility. We're going to think about domination. And then we're going to try it out on a couple mazes. Now, certainly, I'll try the tiny and the small maze here on my laptop, but I'm not going to try the medium maze and the large maze just because it takes too long on a laptop. I do it on my workstation at home or server environment. And so I'll leave it up to you to run this full experiment. Please do, right? So you can see how the theory plays out. And one of the things you'll find is a relationship between how these heuristics that dominate play out with the effective branching factor effectively when you get diminishing returns, right? So I strongly encourage you to tinker with this. It's an exercise, and what you learn from this exercise will be important for future project and future assignment later in the semester. And so one of the pieces of information that I'm using is this algebraic structure called a matroid, right? And if you can show that a particular construct or problem satisfies the criteria for a so-called matroid, then you can prove, then you have proven rather, that the greedy approach is the optimal approach. And so I'm making use of this structure to construct a regular system, so to speak, where I can dial up my heuristics that I'll talk about when I bring up the code window. Okay. So I also encourage you to take a look at that. Matroid is a so-called subset system, and it talks about independence and various properties that demonstrate that greedy will always produce optimal if you can show that it satisfies these properties. Okay. Any questions? No? How's everybody doing? It was pretty quiet, right? Okay, all right. So why don't we pop out of here? And I'm gonna share my desktop. Um, there's another person in there. All right, I'll deal with that later. What just happened? Am I out of Zoom? Um, no. Oh, there it is. Oh, that's the same screen. All right, thank you. Oh, um, but I'm not getting my oh, that's weird. Excuse me for a moment. Why am I not? Okay, that's why. Desktop, share. Um, Curious part about computers, they do exactly what you tell them to, right? No more, no less. All right, so let me bring this a little bit bigger. Okay, so why don't we go through a few sort of loose ends at the outset before we dive into the heuristic and a heuristic and and a parameterizable version of heuristics that can be dominated using what I've implemented. And so we're going to use different mazes, and the mazes are of the sort XXX search. So there's tiny search maze, there's small search maze, there's medium search maze, there's large search maze. It's similar problems, only when you go from tiny to small to medium to large, you're increasing the size of the maze, as well as the complexity of the rows and the passageways and the walls and things like that. So you're using a search agent, and it's going to be an A-star search. And it's going to be a food search problem. So you're trying to, as we had in question 7 on project 2, we're going to be looking for all the food pellets that are inside of the maze world. And the heuristic is called food heuristic, which was one of the things you had to implement for question 7 on project number 2. Okay. All right. So I'll hit OK. And so I'm inside of search agents.py. And again, I stress this is a solution, not the solution. My purpose in using this particular approach is because I can parameterize it for different heuristics that dominate one another, provably so, right? Because of that matroid property afforded by minimum spanning tree. Okay. So we start out and we get our food grid, and I convert it to a list. And then I like to keep around information so I don't have to recalc all the time. And the information I want to keep around, there's some code inside of the search problem that allows you to hold on to pieces of information. So I make use of that. And so I use a dictionary to cache away scores, and those scores reflect the total weight for a minimum spanning tree. So you have a connected component, right, and you construct, and you use a greedy algorithm to associate closest nodes. And by this idea of closest, all of the sub-solutions for minimum spanning tree are going to be, the subsets of that are going to also be minimum by definition of what minimum means. And so that certainly satisfies the matroid property, and I encourage you to look it up. And therefore, we know that greedy is the optimal approach. And so using that fact, I say, okay, well, if I can calculate the weight of a minimum spanning tree, I can calculate the weight associated with what I call a K minimum spanning tree. It's a minimum spanning tree, just assuming K many nodes are in that connected component. Because if I say K is equal to 5, when I go to K is equal to 6, that's still part of the minimum spanning tree because it satisfies the properties of being a matroid. Does that make sense? So minimal things are constructed of components as subsets, which are also minimal. Does that make sense? Okay. So using that fact, let's just first go through the minimum spanning tree. Now, I don't keep around the tree. I just calculate the weights using greedy selection of this notion of closest food pellet each time, where closest is, in this case, I'm calculating that using Manhattan distance. Now, you could use other distance measures. That's fine. Manhattan distance is a faithful measure because it respects the geometry of the environment, mainly navigating around all of the walls and such. Okay. But absolutely, you don't have to use Manhattan distance, and there's no one way to do this. All right. So we start out, and keys need to be immutable. So I wrap that in a frozen version of my set. And then I find the closest food pellet to the Pac-Man, right? You start out and say what's closest to Pac-Man. And then after that, you say, let me construct the MST using greedy approach to select the closest food pellet to that food pellet. Okay. So now I go ahead and I compute my closest, my minimum spanning tree. That's this grayed out one because I have the code live with my modification. And once I get my MST, and I'll show you that method down below, it's going to return back the total cost for traversal of the minimum spanning tree. Does that make sense? All right. So let's go down, and I call it minimum spanning tree in Manhattan. You could call it, if you're familiar with New York, Central Park distance, right? Because there are no trees in Manhattan. But anyways, if you're from New York, you get that. So minimum spanning tree using Manhattan, I have my list, and I start out, and I start adding those points one at a time. So I start out and say, what are the nodes that are in my spanning tree? And then I maintain a data structure that I'm going to use to accumulate distances. When I calculate those distances, those are Manhattan distances using the tools provided by the Pac-Man environment. And I compute pairwise the distance between my node in question and all the other nodes that are available in the graph. Nodes, I'm going to use the word node and food pellet interchangeably, okay? All right, so I go through and I compute all those distances, and then I loop down and I say, okay, have I added all of my nodes to my spanning tree? Have I done that calculation? Yes or no? I keep iterating until I reach that condition. So now I say, okay, what's the closest node to my particular node in question? And I select min, get the key for that to identify the item, and then I get its cost. And then I accumulate its cost. So each time I get a closest node, the greedy approach, and I add it to the tree, I'm going to accumulate the cost of getting to that node, namely that Manhattan distance. And so I do that again and again and again and again until I exhaust all the nodes to make a connected component. Does that make sense? Any questions? No? All right. So I remove that particular node that I've added from my list of distances, and then I recalculate my distances because the new node that I add, now I want to find the distance between that new node that was just added to the tree and all of the nodes that haven't been evaluated. Does that make sense? And so I keep doing that in rounds. Once I update my distance measure, I come back around and I say, what's the closest node now to this node that I just added? And then I update what that just added node is, recalc the distances, accumulate the cost. That makes sense? Any questions? No? So when spanning tree in Manhattan returns, I get back the total path cost, both for Pac-Man to get to that closest food pellet, and then that connected component, the MST, which visited those closest nodes, the greedy approach, and we know greedy is optimal, to construct the total path cost for my Manhattan spanning tree. Question? No? All right, I'm going to get out of here really quick. Okay. So what I've done then is I've created a different minimum spanning tree, and it's a variation of the minimum spanning tree. I call it closest neighbor spanning tree in Manhattan. I like long names. And so what I give it is a neighbor count. And what that neighbor count controls is when I compute my MST, how many nodes, i.e., how many neighbors reachable on that connected component should I add? And so with this, okay, if I say one neighbor, I have the original node that Pac-Man gets to and the next hop along that MST. If I say two, I have the original food pellet that Pac-Man got to. I have the next one and the next one. And so in flight, as I build the minimum spanning tree, I'm cutting off how many of my n many nodes in my state space that I'm adding. And because I know the minimum spanning tree satisfies the matroid property, if I don't finish, quote unquote, the MST, if I were to add the next node and the next node, I know by definition of what closest means that an MST with 6 neighbors is going to contain the MST with 5 neighbors, the same set of nodes, because it's a matrix. Does that make sense? And so if that's the case, if I add the path cost, I know for a fact that Manhattan distances are never negative, right? And in fact, unless a pellet is in the same location, which they're not, because it'd be the same pellet, I know that they're greater than 0. So if that's the case, I know if my MST neighbor approach adds one more node, that can only increase the heuristic value. So I know for a fact that the 1 neighbor is dominated by the 2 neighbor, is dominated by the 3 neighbor. And that gives me a way of parameterizing my heuristic that I know is admissible because it's based on Manhattan distance. And I know that as I increase the neighbor count, the size of that subset to construct the MST, I know that a larger neighbor count version of the heuristic based on Manhattan distance is always going to dominate that smaller neighbor version. Does that make sense? All right. So that was just some way that I said, you know what? I want to be able to parameterize it because in any sort of experiment, you want to have what look like these control knobs, like a stereo system, if you still stereos, right? People look at me strange. What's a record? What's a CD? But anyways, you have these control knobs and you want to be able to have some control that you can turn up and change in a notion of regular increments, parameters. And then with the experiment, what your goal is as I turn this knob, in this case, the level of domination of my heuristic, i.e. the neighbor count, or the size of the subset of neighbors on this connected component, my MST, I want to see what the effect is of turning this dial up and down in certain increments. Moreover, what that allows me to do is as I look at the number of nodes explored, my time complexity, maybe that time complexity will certainly decrease, but at what rate does it decrease? And for certain differences in level of domination, am I going to see diminishing returns once I get to a neighbor count of half of the nodes or three-quarters of the nodes or what have you, right? So in any sort of design, you want to make sure that you build into your system the ability to parameterize the factors that you're trying to understand the impact that they have, the effect on some performance measure. Does that make sense? All right. Any questions? No? All right. So what I've done here is I really, at home I have a 30-inch monitor and I see like a whole page, and it really is harder here with this smaller screen. You kind of get lost in the details um, of where you are. So let's see. All right. So here we are. We are in food heuristic. And food heuristic is called by this version of an A-star search for the food search problem. And we come down here, and the business end of all of this is right here, right? So I've sort of grayed out the minimum spanning tree in Manhattan, and I'm calling closest neighbor spanning tree in Manhattan. And so I'm going to set a breakpoint here, and I'm going to set this back to 1. And let me walk you through a couple considerations for this solution, keeping in mind this is a solution, not the solution. There are many different solutions you could have. You could do all sorts of things like, let me look at the diameter of the graph, or maybe I'll look at the centroid among all of the pellets, or maybe I will, do a whole host of things, increasing bands based on distance as you add more pellets to the minimum spanning tree based on the location. You could do all sorts of things, but this is just one way of doing it because I had the MST already, and I thought, gosh, how can I parameterize this that I can kind of, have a great explanation here in front of the class, okay? All right, any questions? All right, so let me go ahead and I'm going to run this. And this is going to be a little bit slow, so we're going to pause a little bit to let this produce a solution. And so here, the number of food pellets is 83 in the small grid. And so the small grid is up here, right? It's a blank frame. It hasn't updated the display yet. Because remember, in these informed searches in the Pacman environment, you're producing a plan. So you're making an evaluation, you're producing a complete solution, a list of actions, and then that's returned back to the environment. It iterates through that list of actions and updates the display, right? So you just get an empty frame here. And so here, the number of food pellets is 83. And what I do is I am choosing, instead of saying neighbor count of 1, of 2, of 10, I'm going based on percentages, right? And so I pre-calculated when you're 1.25% of the pellets, and I use floor mathematically rather than ceiling. That's a neighbor of 1. So I'm going to construct a minimum spanning tree by adding 1 node to that connected component. It's fairly trivial, right? So I'm going to call that my heuristic H1. And you can imagine in a written articulation of this experiment, I would index each heuristic based on the neighbor count or based on the percentages. So this would be H1 or H sub 0.0125, for example. Okay, so if I do that, let me go ahead and I'm just going to run this. And we're going to watch the console. It takes a little bit of time because it is the worst of all of the family of heuristics that I've implemented through this neighbor count approach. So now we do that and we see the Pac-Man eats all the pellets. Okay, great. But if we look at the number of search nodes expanded, okay, that screen is blank. All right. It expanded 41,337 nodes. Okay, so that's the worst of them. Okay, so let's see what happens if we double that. And I wanted to make my life easy. Um, so let me save and let's run that again. So if we run that again, now we've doubled it. So that means there are going to be a neighbor count of two nodes that we add to this connected component when we construct the minimum spanning tree. It'll still run for a long-ish time, but a little faster than before. And you notice it returns faster. Pac-Man eats all the pellets. And then if we look, we've now trimmed by almost half the number of nodes encountered, 23,801. Okay. And if we were to look at the value of the first one, 0.0125, and the second one, 0.0250, right? Or twice the 0.0125, we'll see that the heuristic evaluations, those H values are always larger. It's always larger because when we construct the MST, we added only a single node to the connected component in the first case, but a second node to the connected component in the second case. And because these things are always positive Manhattan distances, we know that the two neighbor version is always greater than the one neighbor version by definition of a matrix. Does that make sense? So we know that the two version dominates the one version, and we see an almost 50% reduction in the number of nodes that are expanded. Okay, so if we can do that with two, let's try four, and doubling, an exponential, or not doubling, a multiplicative increase in the number of nodes, in the number of nearest neighbor nodes added to the connected component. So let's run this, and you'll see it returns fast. Oh, if I hit continue, it returns faster in the runtime. And again, it finds all of the nodes. And if we look, it's now 9474 nodes expanded. And so this continues. I could continue it on units of one or increments of 0.0125 or whatever schedule of domination, so to speak, that I desire. And so this just shows you, let me try 10 times and let's see how that works. Save all. I know it auto saves, but I like taking affirmative actions on things so that I know that I saved it. So let's try that again. So we'll run it, run, continue, and it returns almost immediately. And you can see that the number of nodes we explored is 599. And so in an experiment for the number of nodes explored, that's our N, and we know the equation for the effective branching factor. So for each parameterization that we try, we know these are all admissible heuristics because they're all based on Manhattan distance when we construct the Manhattan MST. We know that as we increase the neighbor count, that the higher neighbor count, when we construct a larger subset of nodes in the MST, is always going to dominate the lower neighbor count version, right? So we know they're dominating, we know they're admissible, and we see here the theory plays out exactly as we talked about, but then you can quantify this more rigorously by calculating the effective branching factor, B star, for each of these runs. So it'd be a nice chart to show that, okay, for this heuristic, as we turn up the dial, this is how the performance plays out. But this increase for this problem, at least for this maze, does not go on forever. We have diminishing returns. And you can see that at 10, let's try, I don't know, what do you want to try? 12? I don't know. We had 599. So let's try 12. Um, let's see what 12 does. So it was 599 before. Oops, that was pretty fast. It's now 365. Okay, that was a dramatic decrease. All right, so let's try, I don't know, 20. See, 20 times 1 is 20, 83. No, okay, that works. Um, so 3 something, let's see, 298. Okay, so 298. So let's try eking this up a little bit. Let's try 25 and see if that affords us. So it's 298. Save all. Let's try that again. 298. So we've reached an asymptote, right? For this notion of domination. But if we were to change the maze, and I'm not going to do medium maze because it takes a really long time on my home machine, let alone the laptop. So but certainly we see for this particular experiment, as we get to, I think it was 20, let's see if we can, what happens at like 18. So around 20 or so, we reach an asymptote and we don't get any further improvements as we increase the neighbor count, increasing heuristic, albeit it's still admissible and it's theoretically dominating. And so it'd be up to you if you want to explore why to actually track, print out, record the heuristic evaluation values that you see along the way to characterize what's happening. Does that make sense? Any questions? No questions? So I strongly encourage you to tinker with different versions of the heuristic that you've implemented for question number 7 and try this out for yourself. I'm not sure I would run medium maze and certainly not large maze on your laptop. You're welcome to try. There's so many parameters that will impact the runtime. It might take minutes to run on the medium maze. Okay. Any questions? No. So is it an assignment per se? No, it's an exercise, but I strongly encourage you to try the experiment to give you a better understanding of how this domination plays out in reality. And when you do so, take your heuristic. You're welcome to use the approach that I've used. But if you have a different one that you can parameterize, focus on parameterizing your heuristic so that you can effectively control your factor in some notion of regular increments in order to report on what is happening with the effect. Okay? All right. I did have an idea to have something I called the boo factor, and the boo factor would assume that ghosts were in the mix, but that would turn the environment from static to dynamic. But I wanted to introduce some other stuff first before we make it a dynamic environment. But there's all sorts of things you could do. One really fancy one, you could treat each one of the pellets as a magnet, and then you add up all the magnetic flux and you move in the direction of the magnetic flux to guide what you add next to your notion of a spanning tree. You could look at the diameter of the graph. You could compute notions of value bands based on some notion of distance of nearby pellets. You could do all sorts of stuff for heuristics, right? The space is very, very large. But use an approach that you can parameterize because it's much easier to run experiments when you parameterize. And if I were doing this in some sort of report or something like that, I wouldn't be running it in the debugger. I would parameterize it and write a shell script to exercise through different levels of my controllable parameters. And then I would add some printouts that I would then parse out to generate graphs and things like that, right? But think experimentally, think about factors with your heuristic that you can control and set in regular increments and explore what the effect is as a result of them, okay? And as the complexity of the state space increases, you're going to see different profiles for how your effective branching factor plays out, as well as the number of search nodes expanded. And as you go from the tiny maze to the small maze, things are one way. As you go to the medium and especially the large, you're going to see that profile at those regular increments. You're going to see that change. Okay. All right. Any questions? No questions? So please do try it. That's all I had to say for today. If nobody has any questions, more than happy to let you all out early. And I'm just going to head to my lab and do my thing. All right. So any questions? Going once? Going twice? Okay. Sold. There we go. So I'll see y'all on Tuesday.